Okay. So we're back with calculus. Let me open the file for calculus, not this one, not that one. What is this? Also something else. Okay. And calculus 1. So we've started talking about the function analysis theorems.
Sorry, I remembered while we were in algebra that I forgot to tell you to derivate the function we had in the practice session that you told me to remind you.
Which was the which was that?
Not last lecture, the one before that, I think.
Yeah, let's look for it for a second. I remember asking you something, but I don't remember what it was exactly.
I can look for it while you start and
No, I'm looking for it now already up there. Ah, uh, just a second. Yeah, it's a very good example to start with as well. It was we needed to show that something is decreasing, right?
yeah.
Was this example here?
Yeah. You got to one part that you had to derivate to uh, here. Yeah. We were trying to find if the sum converges or not.
Yes. And just a second. I remember. Yeah, exactly this one. Okay. So we want to show this function is decreasing. So we'll start with an example, and then we'll move on to the theorems. And I remind you in general that this is the kind of things we wish to do. The first example I've shown you last time was whether or not e to the x equals x ever. Say move everything to the left-hand side, you get one function, and then you study it. And in this case, we studied and showed that it has a minimum value which is 1, which means that it's never 0, therefore there is no solution. I also asked, well, here, what about e to the x equals x plus square root of 2 or plus 1? It's the very same idea in solution. The minimum here will be 1 minus square root of 2, which is negative. And then you know what? I wish to start with that example and then I'll go to the one you reminded me of, but I won't forget it because it's written here. So example, how many solutions does the equation e to the x equals x plus square root of 2 has? So has or have, solution. First of all, we move everything to the left-hand side and build a new function. And our question is whether or how many times actually does this function equal 0? Do you agree so far?
Yeah,
Okay, thank you, Thomas.
glad to help.
The derivative is exactly the same as the last exercise, because the only difference is that constant here. and the derivative of a constant is 0. So the derivative is the same. And again, like the example from last time, the function has a minimum value at age of 0. But what is the difference? But here, what is the value of age at 0? It's 1 minus square root of 2, which is a negative number. So we know that the function age has a negative y value. What does that tell us about how many times age equals 0? Help anyone. We know the y value of age is
Oh,
negative.
because it's negative, then it goes to positive in both sides. Then
Why does it goes to positive in both sides? And how do we know that? By calculating, when we cannot substitute, we calculate limits. By calculating the limits at x goes to plus or minus infinity, we can show that age tends to infinity. From different reasons, but that's true in both cases. Therefore, age switches twice between negative and positive y values, and so has two distinct roots. When age at minus infinity to 0, age has exactly one root since it decreases, and another root at 0 to infinity. So many of the things I'm saying now are due to theorems that we're supposed to learn today. Okay, and also calculating the limit needs L'Hopital rule, which we will learn next session probably. Okay, so the exact details, I won't say that. More details of that answer will be possible later. Okay, just wanted to show you the general idea to solve questions using analysis. The first question was easy because the minimum was 1, so the function is never 0, like you see here. And the second question, that's the one with the square root of 2, you see the red function age goes below the x-axis, but it is super important that afterwards it tends to infinity or a positive value to make sure that it goes down from positive to negative, therefore intersect with the x-axis. becomes negative, then go back to positive. Okay. And lastly, and that yes, Thomas.
Yeah, just a question. This is a very particular case, right? Because like you chose to
Wait,
check the
Thomas.
limit.
The general idea is finding when does the function increase or decrease, and what are the values of the function at the ends of the segments where it increases or decreases. So the general idea here is saying this function decreases from infinity to the minimum, then goes from the minimum up to infinity. And knowing that, you can know whether it passed through the x-axis or not. So the general process is not particular. That's what we do in a lot of cases. The particularities are the fact that it increases and decreases, and the minimum values and the limits at the ends. All of these can change.
Yeah, no, my particular question was for you knew that at point zero it was negative, and then you showed that the limits for minus infinity and infinity were positive. That only means that there's at least two roots, right?
So again, I answered you that question. I'll reiterate and say specifically, I didn't knew it was negative. And in the first case, it wasn't, right?
Mm-hmm.
I found out that it's positive, and then I didn't even find the limits because it was irrelevant, because the minimum was 1. Here, when the minimum appeared to be negative, I had to make sure whether it goes afterwards to positive or not, because there could have been an asymptote below the x-axis, and then there was no further root. And lastly, the fact that I'm saying that from minus infinity to 0 there is only one root is because when the function is decreasing, it cannot, after passing the x-axis, it cannot go back again. It's 1-to-1 over the segment of monotonicity.
Okay.
Okay, but I'm mitakesh, but I insist that it is not particular. That is always what we do. What changes are not always, but most times. But what changes are the function. But always I try to see when they're increasing, when they're decreasing, and what are the values at the ends of the segments of monotonicity. Okay. And I wanted to say I won't write it, but just by heart. If we've taken this function, then age at 0 is exactly 0, meaning that the function decreases, meets the x-axis, and then increases again. So there is only one root, which is the minimum value. Okay. So now let's try working with this. And the question is this function decreasing from some point forward? Because that's what we wanted. We wanted the sequence to be monotonic decreasing, and a finite amount of elements do not bother us. By the way, I said next session. I was confused. In linear, we have 1 session a week. In calculus, we have 2. So we'll do a bit more than what I just said. But not more subjects. The subjects are the analysis theorems and L'Hopital rule. Just I'm not sure when I start L'Hopital. Maybe this week, maybe the next one. We'll see how it goes. Okay. So in order to know when does the function decrease, we need to derive it. By the way, that is one of the analysis theorems that we did not learn yet, but we know it from high school. So I'm allowing myself to say that if the derivative is negative, the function decreases. But that's actually one of the theorems we need to prove. Okay, so let's derive it. Does anyone remember how can we derive such a function?
The chain rule.
No. It's a power of functions. It's an exponent. So the Ilan rule, we say it's e to the ln of this horrible thing, prime, which is e to x squared times the ln of 1 plus 5 over x cubed prime. Quite horrible. And which is equal to, so now the chain rule. The outer function is e to the x, so it remains the same, times the inner product. What is the inner function here? Let me write it. So the outer function is e to the x, the inner function, its derivative is e to the x. What's the inner function here?
X squared, the logarithm of
Power, exactly. X squared ln 1 plus 5 over x cubed. And its derivative is 2 times x times the ln plus x squared times the derivative of the ln. And how do we derive a ln? It's also a chain rule. I will do that as such. And the derivative of that, that's x to the minus 3. So it's minus 15 over x to the 4. Such a nice derivative. So we take the inner function and we plug it in within the derivative of the outer function, and we multiply. What was the coloring then? Green. And we multiply by the derivative of the inner function. That. Okay. Now, so we get that's the outer function derivative times this monstrous thing. Now, we are interested in the sign of that thing. This is always positive. So we can work with what remains. This is positive. So we will just work with that expression. And what can we say about it?
It's ugly.
So first of all, x squared over x4 is, we have x squared here. And that equals x squared. So that is x squared plus and that's minus 15, and that's 5 over x. Okay, so that's what we have. Can anyone guess how can we find if that thing is negative or not? The usual way is to equate it to 0. I'm not sure equate is the word, but find out when is this 0, and then find afterwards whether it's positive or negative. Here it's too complicated to solve for which x does that equal 0. It's impossible. Can anyone else guess how can we be sure if that is a negative from some point forward?
If it's negative, if minus 15 over the, x squared plus x divided by 5 is smaller than the other side,
First of all, this is definitely negative, right? But this is positive. So you're correct, Thomas. I had an idea in my head, by the way. Now I'm seeing that it doesn't necessarily work. So I'll just tell you what was the idea, and if it works, it works, and if it not, I will stop going this way. But my idea was I'm trying to do it in my head for a second. If I multiply and divide. If the limit was negative, then it was negative. Okay? But I'm not sure the limit is negative.
It's not going to be negative, I'm pretty sure. But
is it 0?
No, because you have 2x. You have 2x that is increasing.
No, that doesn't matter. Let me just make sure for a second what is the answer before I do more calculation. It's 0, yeah, sadly. Okay, that's what I thought. Well, I saw it later. I didn't think it from the start. So that thing goes to 0.
Right.
Therefore, it's horrible. What else can we do? I'll do a couple of checks, not to waste any of your time, because I'm not sure what is the correct step. First of all, we see it's negative, but that's not a proof at all. What's the limit here in the numerator? Maybe that would be enough. So x is infinity. That's infinity, infinity. I think okay, I'll take a chance. I'll move a bit forward with it, and if it doesn't work, then I'll stop. That is 2x ln of 1 plus 5 over x cubed minus 15x over x cubed plus 5. That equals, remember, the question is supposedly easy, supposedly high school level. We're just asking that's actually that the reason that I'm continuing with this is because that's actually a function analysis question. Our question is this function negative since some point? Using the grapher, it seems as though it is, but that's obviously not an acceptable answer. This graph, what is this? Yeah, no, it's the same thing. But that's what we wish to do. So what I'm going to do next is a common denominator. We get x cubed plus 5 here, and here we get 2x, x cubed plus 5 times the ln of 1 plus 5 over x cubed minus 15, and I'll take x as a common factor. And all these are
Minus
positive.
15x. Oh, wait, never mind.
Yeah, I
Sorry,
took
my
the
bad,
x
my bad.
factor. So I'm left only with this. And this tends to, well, if it's 0, it will be so completely annoying. But I think it does not tends to 0. And the limit itself, I might tell Tomas to remind me again, because we need L'Hopital there to actually calculate the limit. But first, like I said, let me find out if it's true. Yay, it's -5. Lucky us. Okay, so this goes when x goes to infinity to -5. Therefore, it's negative since some point. We will be back to the limit later. So I'm glad I took it to fruition, because you've seen what function analysis looks like. None of the tools were actually new, but the way we think about things changes. In high school, we are used to solving these questions algebraically. I wish to know when it is positive or negative, then I solve an inequation. But I'm not able to solve such inequations. So I use limits. And I know that if the limit is -5, then from some point forward, it must be always negative. Okay? And the problem was that the first limit was 0. And if the limit is 0, then I'm not sure if it's positive or negative. But then I did a common denominator, and x is positive, and x cubed plus 5 is positive in the positives when x tends to infinity. And we were left with this expression, which tends to a negative number. And and again, solving this limit, to be honest, you don't have to use L'Hopital, but you know what? Let's do the limit as well, because we learned it, actually. Believe it or not, we do know how to solve this limit. So I'm correcting myself. I won't be back to the limit later. Now is later. What's the limit as x goes to infinity of that? So first of all, let's separate it into two limits. It is the limit as x go to infinity of 2 times x cubed times ln of 1 plus 5 over x cubed plus 10 times ln of 1 plus 5 over x cubed. Now, what is the limit of that?
0.
0 because it's ln of 1. That tends to 0. So that's is not interesting anymore. So we are left with the limit of this expression. And why did I say that we are able to calculate it without L'Hopital rule? Does anyone does it ring any bell for anyone? This structure here, specifically this. Not all at once.
It looks like the
Yeah.
1 plus 1 over x, no?
In a way, yes, and in a way, no, you're correct. We used what you said within the calculation of that limit, but I'll remind you that wouldn't it be nice? This is the limit we've learned about. I'll remind you where.
Yeah, that's 1.
Exactly, that's 1. Where was it? Before that, when deriving log, we saw it almost here. Remember this? So when the log, when the a is e, it's simply 1. Okay, so that is 1. And whoever solved question 1a from my tests ought to know this, but I didn't finish the wouldn't it be nice? That's not what is written. What's the difference between what I wish and what is actually written?
The 2x to the power of 3, isn't there?
The x to the power of 3 is there. That's that. So there is a 5 that we added to the denominator, and there is a 2 that we omitted. This goes to 1, so what is the limit altogether? And now you can see why the whole limit is -5, because this part goes to 10, -15, it's altogether -5. Agreed?
I'm still not fully understanding where the x to the power of 3 went, because you have 2x power of 3.
Yeah, the x to the power of 3, I moved it to the denominator.
So okay. Yeah.
See?
Yeah, no, I didn't understand because it was in the denominator, but it's in the denominator of the denominator, so it's in the top
Yeah.
part. Okay.
Yeah. It will also be a method when we learn about L'Hopital. It will be a very known method that if we have infinity times 0, we move it to the denominator just as I did now. Okay, so it will be a known method later. In any case, we calculate the limit. I'm wondering, I'll take 5 minutes of your time to ask ChatGPT how he would have solved this question. Wonder if he'll give us a correct solution, and I wonder if he finds a simpler solution than the one I had here. Is this function decrease from some x value forward? So first of all, it looks at the limit. I agree with that. If the limit was infinity, then I won't say it's decreasing. This is interesting. Instead of saying 1 plus 0 to infinity, he says 1 plus tiny in the power of big. I'm not sure if it's better or worse, but it's interesting. Whatever, he did the ln. He got to the derivative. We did ooh, I made no, that's the same thing I got, right? Seems different here, but I wonder where did I make because it was x squared times that. Okay, great. No, it's the same. Yeah, it's the same that I got. We observe the limit. Okay, so this is horrible. This is not allowed at all. Can you articulate that? That's a mistake students do. Can you articulate exactly what it is in this step? Just here.
He took out the x squared over x squared, but he took the 5x and just threw
He
it away.
ignored the 5x. He said that's negligible. So that's that. And then he said the derivative is about that. And he also, you know what? It's not too horrible. One can, okay. If this was on a test, I would mark it down definitely. But he does calculate the limit I did. You see the -5 here. He does calculate the limit similarly, just he does it in a non-accurate manner. Okay, we do not allow to neglect because maybe the stuff we neglect changes drastically the limit here. Here, because it's 10 and 15, it actually works, but I don't like the arguments. But yeah, surprisingly, the main thing, the main way is very similar to what I perform. So I use the ChatGPT also to teach you when to show you when does it make mistakes and it's not completely accurate, but also for you to understand how such seemingly simple function analysis questions require a very good control of analysis ideas, because not usually the algebra does not work, and then we have to have a good fluent calculus language in order to work through all that. By the way, when you took ln of f, that's exactly the equivalent of the Ilan rule, which I use, right? So really, it's all the steps. Okay, fine. So we solved this, and thank Tomas for forcing us to. Where was this question for? A test? It was from a test. I'm betting now that not single student has solved it in that test. I don't remember if my name was on top of that form or not. If so, then shame on me. But also funny. Okay. And it is solvable, but it's a very long way to solve the entire thing. Okay. So now we will start stating analysis theorems, and later we might prove some of them. But mostly I will give examples that's like you saw. The most important thing for me is for you to have the ability to work with the functions and analyze them. That's the idea. It goes together with understanding the theorems, but given that we don't have a lot of time, it's more important for me for you to be able to actually do analysis of functions. Fine. Okay. What would be the first theorem? So the first theorem is the mean value theorem. The mean value theorem. Suppose f of x is continuous at the segment AB, including the ends of the segments A and B. Also assume that f of A is smaller or equal to 0 and f of B is larger or equal to 0. What do you suppose the mean value theorem states? The y value at A is below the x-axis. The y value at B is above the x-axis.
That it's 0?
Then there exists a point C within the segment such that f of 0 equals 0. F of C, sorry, equals 0. Yeah. So we used that implicitly in high school. We used it implicitly before. Remember when I told you about the age here? I told you, oh, it's negative at 0. It's positive afterwards. So between them, there is a root. There is a intersection with the x-axis. That's the mean value theorem. Okay? But don't forget, continuous function. If the function is not continuous, it can jump above the x-axis, but if it's continuous, it must intersect with it. Agreed? Example. Every positive real number has an nth root for any n. So roots exist like square root of 2 or the cubed root of 21. Why is that? Why is that a consequence of this? Hold on to your hats. Proof. What does it mean that the number has an nth root? So given a positive number A, we wish to prove that the n root of A exists. What does it mean?
It's in the real numbers?
No, but yes, yeah, I do mean that. But what does it mean, the nth root? It's a number such that
Multiplied by itself n times.
i.e., there exists a number, let's call it C, which ought to be the nth root, such that C to the n equals A. Do you agree? So we need to prove that this equation has a solution. What are the slogans? What are the mantras? What do we do? We
Just-
move,
I was going to say a
Yeah.
logarithm, but yeah, sure.
yeah, we move everything to the left-hand side and build a function, i.e. c to the n minus a equals 0. We will analyze you're right, analyze. With S and not Z, surprising. Is it surprising?
Depends on the country.
Oh, really? Okay.
Yeah, if you're
And-
stupid like an American,
So if you're English, you would write like this?
If you're American, you would
if you're American, you use Z, I believe.
So the English write S. Oh,
Yes.
so I'm stupid like an American. Okay. So we will analyze we'll analyze the function age of x equals x to the n minus a, which is continuous, So what is age of 0?
It's minus a, no?
It's minus a, which means that it's positive or negative?
Negative.
Negative. So in order for it to have a root, we only need to find some positive value, right? What's the limit as x goes to infinity of x to the n minus a?
Infinity.
Infinity. Therefore, we have a positive and negative values. I don't like the grammar here. We have a positive and a negative values of age, and by the mean value theorem, it has a root. Agreed? One can do more than that and even find the number of roots, but I don't mind about that. Okay. So that was the mean value theorem. Next.
Sorry.
Yes.
How can we generalize it to being x to the n and finding the limit to infinity? Because like x is supposed to be a root of a, right? So
No, that's the whole thing. C is the root of a. It's you're writing the function, you're studying the function x to the n minus a, not just the roots, the entirety of the function. And at some points, it's easy for you to plug in. By the way, instead of limit, I could plugged in a, and then we would have gotten a to the n minus a, which is also can be helpful. But then I would have to verify if a is larger than 1 or smaller than 1. That's easier. But in any case, you're looking at the graph of the function. Let's take an example, like let's say the cubed root of 21, like I said. So you take the function age of x, which is x cubed minus 21, okay? At 0, it's negative 21. At infinity, it goes to infinity. X goes to infinity. X is not the solution. But since it moved from a negative value to infinity to a positive value, you're sure that at some point or another, it passed through the x-axis. And that's the root. That's the point you're looking for.
Yes, my question is more about how can we generalize this in such a way, because we are trying to prove that C is positive, right? That's the whole idea.
First of all, I wanted to prove that some number exists, not that it's positive. But
Okay.
by the way, we did prove that it's positive. Why? Because at 0, the y value is negative. And when x goes to infinity, it's infinity, meaning that it's going to be positive after 0. Do you agree?
Yes. Okay.
So between 0 and some point, there must be a root. So the root is positive because the root is between 0 and some positive points afterwards.
Okay.
Right? Look at the points, not the whole graph. That's basically what we're doing. We're looking at 2 points. One of them is a 0, comma h0. That's the point here. And then now it's going to be a bit of a guesswork, but let's take 5 and age of 5. That was too much. Let's do 4 and age of 4. Also too much. 3 and age of 3. I want it to be on the screen. Great. Okay, you see, Thomas? I know that the function h goes from this point to that point continuously. What must happen in between?
It has to cross the 0.
Yeah, exactly. And it's between 0 and 3.
Mm-hmm.
Agreed? So we did prove there is a positive root for the equation, to be honest. Okay? Fine. Next. Weierstrass theorem. If f is continuous at AB, including the ends of the segment, then f gets a minimum y value and a maximum y value at AB. It couldn't be unbounded, and it actually gets at least one x value, a maximum in the y value, and at least at one x value, the minimum y value. Okay, it goes between two different values. For example, consider f of x equals x and squared minus x to the 4 at 0, 1. The theorem Weierstrass promise that f has a maximum and a minimum value. Just a second. אלנו, נא לעצור. כרמלי, יש שם עניין במטבח. תתערבי, כי אני לא בטוח. היא אמרה, אתה רוצה שאני אמות. Okay. You wanted to close the door, the refrigerator. He said, you want me to die on the refrigerator. Okay, so, sorry. The theorem promises that f is a maximum and a minimum value. How do we find these values?
When the derivative is 0.
That's it. So that actually would be the next theorem. You're correct. So let me say it like this. We know, since we know these extremum exists, we wonder where could where on the x-axis they can be. The next theorem will help us, and then we will get back here. Okay? So Fermat's theorem says the following. If f has a local extremum, and I'll write the exact definition in a bit. If f has a local extremum at x equals x0, and f is differentiable at x0, then what must be the derivative? Like you said?
0.
0. That's Fermat's theorem. Note a local extremum is a point x0 such that in some area x0 minus epsilon, x0 plus epsilon, the highest or lowest value of f of x is f of x0. It's the highest or lowest point within some double-sided area. So, conclusion, if f is continuous at AB, it must have a maximum or minimum, not all, and sorry, maximum and minimum points. Where could they be? They could either be at an x value such that the derivative is 0, or f is not differentiable. Which function do you know is not differentiable yet is continuous?
The third root of x or something?
The what?
The third root of x.
Well, that's true. Which is the simpler one, though?
Modular.
No, modulo is not a
I mean, just
function.
absolute value you said, but yeah.
Absolute value, yeah, absolute value.
Well, that's,
And
is
and
that
the
not the same thing?
as what?
Modular.
What absolute value and modulo? I don't think so. Modulo is
Modulo is remainder.
in number theory.
My teacher from high school called it the same thing. I think it's because he was Romanian.
Yeah, I don't think in any language that I know. In computer science, modulo is the remainder in the division of integer numbers. That's what I know to be modulo. In any case, absolute value. And the absolute value actually has a minimum value where the function is not differentiable. So that's exactly where the minimum is hiding. Okay? Or what other option there is? It's easy, to miss, but it's important not to miss it. So either the derivative is 0, or the function is not differentiable altogether, or what is the third option? The edges, x equals a or b. Because in the edges, it's not a local extremum. It's not a double-sided area. The function could go straight up and got to its maximum because it's the edge, not because the slope became 0. So all these points are suspect, and then we check all of them. Let's get back to the example. Getting back to the example, the function was x squared minus x to the 4. The derivative, it's always differentiable, so we don't have this problem. The derivative is 2x minus 4x cubed, right? And when does it equal 0? X times 2 minus 4x squared equals 0. Then either x equals 0 or x squared equals half, meaning x equals 0 or 1 over the square root of f, or 2, sorry. Why didn't I take minus the square root of 2?
Because we were positive in this case?
Yeah, we are between 0 and 1. We need to find a number within the bounds. Okay? And what other point is suspect?
Zero, one.
1. 0, by chance, was also a point where the derivative is 0. But we need to always add both of the edges of the segment. So here 1 was not mentioned. So now we know that one of them is the maximum and one of them is the minimum. So now we plug in the suspect points to definitely find the max and mean values. The theorems promise us they exist. We only need to find where are they. And we are sure that they have to be in one of the suspect points. So one of these points is the maximum, another is the minimum, and the third one could mean nothing or be a duplicate of either one. And so f of 0 equals f of 1, they're both equals 0 because 1 squared minus 1 to the 4th is 0, and 0 squared minus 0 to the 4th is 0. So that's that. What is f of 1 over square root of 2? So that equals a half minus a quarter, right? Because when I square it, it's half. When I take it to the power of 4, it's a quarter. And altogether, it's a quarter. So what is the maximum of the function within the, and that's an analysis question. It's actually, it's specifically, I wish to show you. I'm teaching Chedva Shtayim for engineering, and in their quiz, that's where I got it from. I asked them about this question. So that's a bit more complicated because I simply plugged in n equal 2 for you. They had to solve it for a general n. It's not much harder, but still. And they had to find the maximum value, right? So it's calculus 2, but they needed basic calculus ability to solve it. So you don't know why finding the maximum will help answer that question. You will in calculus 2. It's in your syllabus as well. But my point is they had to know how to find the maximum. Some of them got stuck with it, but most of them solve it, I think. And the value is indeed a quarter. And now let's see. So this is the maximum, obviously, because it's the largest. And this is the minimum because it's smallest. And now if I'll draw the graph within 0 and 1, if I write f of x equals if x is between 0 and 1, then x squared minus x to the 4. So that's the drawing. First of all, does it match what we've found out? So at 0, it's 0. At 1, it's 1. There's a maximum here. Where is this point? Where is the maximum? What is the x value here?
1 over root 2.
Exactly. Right? And what is the y value there?
1 over 4.
Exactly. You see, we actually find out things this way. Okay, and I didn't use the graph at all. I only use analysis tools in order to solve this question. That's one of the main things I wish for you to understand. Any questions thus far? And just for general knowledge, if it interests you to know, if I take, I don't know, x to the 10 minus x to the 20, the location of the maximum moves. I don't remember exactly what it is. I think it's the nth root of 2. Let me make sure. So it's 1 over 10 in this case. Yes. but the height is always a quarter. So that's kind of like a nice family of functions whose height is always a quarter, but the maximum point goes to the right. It tends to 1. Okay, so that was just for general knowledge. But in your exam, I may as well ask you to find the maximum value of this function, and you can use the parameter n within your answer. Okay, so that's definitely something that can be part of Calculus 1. Okay, so the next rule, the next theorem, sorry. Lots of French name from now on. I'll tell you the list. So we have Fermat, then we have Rolle, then we have Lagrange, then we have Cauchy, and then we have L'Hopital. It's 5, but remember it's 6. I think I counted. I'm not sure what I'm kind of, what. Taylor, I think it's the 6th, but we don't study Taylor in this semester. So like I said, Fermat we did. So we have Rolle, Lagrange, Cauchy, and L'Hopital. Okay, these are the rest of the theorems. Let's move on. What does Rolle theorem goes like this. Assume f is continuous at a, b. And assume that f is differentiable at a, b, not necessarily including the edges. Then if f of a equals f of b, then there exists a point C between A and B such that f prime of C is 0. If we started at one point and ended at the same point, then the derivative must have been 0 at some point at least. Can you guess why the arguments of the proof of this theorem? I've started at one height and I ended at the same height. What must have happened in between?
There's two cases. Either it's a continuous function and it's always the same thing.
No,
No.
you mean, I think, you mean not continuous,
Constant.
but, yeah, exactly, constant function,
Constant
right?
function, sorry. So it's the same thing and it's always 0. Or,
Right.
At some point it went up, but it went back to the same point in FB. So it has to go down at some point. So it's 0.
So you're correct in general, but using the theorems we learn it's easy. Because Weierstrass promises a maximum value, right? So if the maximum value is at the edges, both the maximum and the minimum, then it means it's constant. And if either the maximum or the minimum is not at the edges, then it must be a local extrema, and therefore the derivative is 0. That's exactly the proof for Rolle's theorem. So how Rolle help us? Because for students, they usually tell me it just seemed like Weierstrass theorem with extra steps, because Weierstrass already told us there is an extremum. So why do I need to say again that the derivative is 0? So two answers I have for it. First of all, I think the most important one, all the following theorems relies on Rolle's result. So that makes it a very important theorem. That's one answer. And the other is there is a specific case one can use in which one can use Rolle's theorem directly to get an interesting result. And I'll give you that in an example. The polynomial px, which equals x to the n, plus an minus 1, x to the n minus 1, plus blah, 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 a1x plus a0, has at most n distinct roots. Polynomial cannot intersect with the x-axis too many times. At most n times. First of all, does that make sense to you? So why is it true? The full accurate proof is done by induction. I won't write the full induction, but rather the idea behind it. The proof is done by, maybe I will write the full version, induction. The case n equals 1 is trivial since x plus a0 has exactly one solution. Agreed? X equals one root. X equals minus a0. That's the root. It's solvable algebraically quite easily. Okay? Assume the statement holds for some for some value of n, we must prove it is true for n plus 1 as well. Assume by contradiction that p of x that equals to x to the n plus 1 plus a n x to the n plus a0 has at least n plus 2 different roots. C1, which is smaller than C2, which is smaller than C n plus 1, which is smaller than Cn plus 2. All of these roots of the polynomial. PC1 equals P of C2 because they both equal to what?
0.
0. Then what Rolle's tells us? Then by Rolle, and there exists D1 between these 2 points at which who is 0 what Roll told us, that is if the function is equal at the end and the ends of some segment, then
There's a
what
local maximum or minimum.
But that's not what Roll says. That's what Svarstra says. What does Roll specifically, explicitly say?
That there's a value such that the derivative is 0.
The derivative is 0, such that P prime of D1 equals 0. And similarly, there exists D2 to Dn plus 1, all at which the derivative is 0. But what is the derivative of the polynomial?
It's
N plus 1 x to the n
mhm.
plus a1. Agreed? How many roots could it have? What is the maximum amount of roots allowed by induction?
N plus 1.
No. We found n plus 1 roots, but the induction claim is that a polynomial of degree n has at most n distinct roots. That's our assumption. Argument. This polynomial must have no more than n roots. Contradiction. So if the above polynomial has too many roots, the derivative has to have too many roots. For instance, if x squared plus bx plus c had 3 roots, then by Roll, the derivative 2x plus b has 2 roots, which is absurd because it's a straight line. Okay, so that's the induction argument. Any questions up until now?
Kind of.
Yes? No? Yes, Sammy?
I don't really understand the proof too much, but I think I'm too tired to understand it right now.
Okay, so I suggest you try to follow it at home and then get back to me at Thursday.
Thursday?
If you don't, Sunday, sorry. So this is the second class we have this week. So again, I lost the class. I earned a couple before, now I lost one, but I'm still up one. We have 2 more classes. It's fine. We'll finish the material in the next one, and the third one could be a review on Sunday. And in that note, I think we had enough for today.
Just a question. I don't remember what the university said, but I also don't care that much. In theory, the classes from next week would be not in the exam.
Yeah, I know.
Again,
I hate
I
it.
don't care. Our exam is in
Yeah.
more than a month, so yeah, I particularly don't
No,
care.
the real problem is I'll be 100% honest with you. I don't care doing less in the exams, but I know that if you don't study it, you won't know it, and then you get screwed in calculus too. So I leave it up to you as a group to talk to me together on Sunday, and if you insist, then I'll say the material is up to now, but I don't think it's a good idea. Also, I nearly finished everything, to be honest. So it won't matter that much. And L'Hopital you want. So I think it's really doesn't matter, and I will finish on Sunday. But if someone has a problem, you're welcome to talk to me and we'll decide what to do. But again, the material we cover in these few classes is quite important for the future because that's actually function analysis. We did all the heavy lifting before, and now we get to eat the fruits of our hard labor. And it will be a shame if we'll skip it. Okay, so if you have any problem, you're welcome to speak to me at Sunday.
Okay.
Okay.
Thank you.
Thank you very much. And see you guys.